Okay, maybe it's late enough to slowly get started. So the reading for this week was the final chapter, which tried to sort of synthesize just kind of the landscape of SNARKs, the pros and cons of the various design techniques, and just kind of give a coherent overview of what the design techniques are. Yeah, I'm curious sort of how understandable it was at this stage you're reading, because it refers to some concepts we haven't talked in great detail about yet. But we probably hit the main things at this point. You sort of know what a polynomial commitment scheme is meant to achieve. You know what an interactive proof is. We haven't really used the phrase polynomial IOP yet, but it's like some kind of generalization of an interactive proof. And those are the two components of most SNARKs. So yeah, I'm curious for feedback on that. But yeah, I could give my, just like a verbal overview of the chapter. And then I thought I might try to give a little sense of, at a technical level, where some of these trade-offs are coming from some of the approaches. But maybe I'll just start by seeing if anyone wants to ask any questions before I give an overview of kind of what the chapter says, and then sort of dive into some under the hood details that are not directly discussed in the chapter. Anyone want to ask anything? Okay, then I'll sort of give my overview. Feel free to write anything in the chat, or just unmute yourself if you decide you want to ask something. Yeah, so I guess kind of the most well-known SNARK out there is growth 16 at this point. Of course, as soon as I try to write something. Okay, there we go. Growth 16. So this is kind of what more or less, I guess, people have settled on, the particular like linear PCP based SNARK. That people like to use, because it's really the winner, like kind of the absolute winner on proof size and like verification cost. Just what the verifier does. So the proof here is only 3 elements of a pairing friendly group. And the verifier does, I don't remember exactly what it is, but like 3 pairing operations, maybe, and something like that is the dominant cost of the verifier. Assuming the public input is small. Yeah, I guess I don't need to dive too deeply into the details of what that means right now, but yeah, we discussed like what is a public input last meeting, like in the context of evaluating a hash function, the public input might be like sort of part of like an initialization vector, like part of the description of the hash function, that sort of feeds into the circuit that computes the hash function. Like you need to know, the initialization vector and like both it's not some secret information known only to the prover. So there's a kind of a cost to process the public input that the verifier has to do, and then a cost to check the proof. And assuming the public input isn't too large, and it's sort of the cost of checking the proof that's dominant. I'm pretty sure in growth 16, it's like 3 pairing operations that are roughly the bottleneck, and maybe there are a couple exponentiations at group X if it's a multiplicative group. Anyway, and perhaps the big downsides of growth 16 in terms of in practice, the main one is circuit specific trusted setup. Right. So this means if you like want to change the circuit you're dealing with, which sort of protocol designers, like as they develop their protocol and make changes to it, they probably wind up changing the circuit many times. And although, every different application has a different circuit, certainly, like Zcash deals with different circuits than rollups and so forth. And so these trusted setups are annoying to run. They're just kind of complicated. So people don't like this. Like if you knew for sure that you're never going to change your circuit, then maybe this isn't such a big deal. But And yeah, this stuff is fairly expensive for the prover. So I'd say P fairly expensive. You know, if you're dealing with a circuit beyond, I'm going to say like 30 million gates ish roughly, I think you're gonna be using a lot of space, you know, gigabytes of space, and prover's kind of slow. It's doing these big FFTs and stuff. So to address this circuit specific trusted setup, you know, there were some things people tried that I don't think really worked very well. Like you could just use a universal circuit that sort of takes as part of its input, like the computer program or whatever you actually care about, and like kind of both compiles that computer program into like a program specific circuit sort of, and also evaluates the program on like the witness and any public input. But the overheads of that like are not good in practice. So people will just not use Growth 16 if they don't like this circuit specific thing. Like, you know, the universal circuit approach just has really high overheads, because then you're feeding like program compilation like through the proof machinery. Like that doesn't feel like something you want to do. So the next sort of class of SNARKs, which are really popular these days, are Plonk and Marlin. These are both based on constant round polynomial IOPs. That's sort of, I think, I sort of settled on that terminology to refer to them because I think it's the most precise, even though it's a mouthful. This is sort of the underlying information theoretic object underneath these SNARKs, and they combine those polynomial IOPs with something called the KZG polynomial commitment scheme. All right. So basically, all SNARKs are obtained by taking a polynomial IOP, that's some kind of information theoretically secure protocol, and combining it with the polynomial commitment scheme. And even the one exception is these linear PCP-based SNARKs like Growth 16. But even the linear PCP-based SNARKs, the crypto underneath them is very similar to KZG polynomial commitments, to the point of like almost feeling like the same thing. So like I sort of have no problem kind of saying that all SNARKs are obtained by sort of, you know, polynomial IOPs by plus polynomial commitment scheme, even though it's not quite true, just because what's happening in the linear PCP-based ones is so similar to KZG polynomial commitments. And the big benefit of this is it's a universal trusted setup, which means a single trusted setup is going to work for like all circuits of a given size, or at most a given size. So you don't have to run a new trusted setup every time you change the computation. You know, so like, I guess the Zcash folks, a bunch of people have run trusted setups, and like literally everyone in the future can just use them, even if they're totally unrelated applications, unless their circuits get too big. In a sentence, like what these trusted setups generate, the structured reference string is the following. So there's like some secrets, right? So you're dealing with a group, cryptographic group G. It's got to be pairing friendly for these SNARKs of prime order P. So it's like, we haven't talked about groups, but the order of the group is the number of elements in the group. A group is just like a set equipped with a multiplication operation if you're treating it as a multiplicative group. And yeah, the trusted reference, the structured reference string here, effectively it picks like a secret value on tau at random between, it's like the number between 1 and P, let's say. I think that's a correct statement. And the SRS is just, there's some designated group element G. Typically, it's just G is selected at random and tau is selected at random, but here tau is what's called the toxic waste. It's called, or the trap door is how some of the cryptographers refer to it. And the structured reference string is just G to the tau squared. So it's G to the all powers of tau up to some bounds. I don't know, let me just call it capital N. So that's what the structured reference string is in these SNARKs. And the situation is that anyone who knows tau can forge SNARK proofs, can like create convincing proofs of false statements. So it's important. This is why the setup is trusted. It's important that no one actually knows Tau. So people have developed these very nice, kind of secure multi-party computation protocols where a whole bunch of people can get together, and sometimes they're called ceremony, and they basically compute the SRS in a way that no one will know Tau unless every single person engaged in the ceremony is like lying, cheating, colluding. They all work together to know Tau. Yeah, and basically, like, Planck and Marlin, they both have this SRS. Like, pretty much kind of any SNARK you sort of come up with, this is a very natural. And whenever you're dealing with univariate polynomial-based techniques, which these constant round polynomial IOPs are based on, like this sort of thing comes up. And the point is that if you want to evaluate a polynomial, without going into any details, if you want to evaluate a polynomial of degree capital N at Tau, then P of Tau, if the polynomial is P, like, if P is a degree N polynomial, that means there's some coefficients of P. So that P of Tau is like, the I coefficient to P times Tau to the I. And what that means is that through like what's called homomorphism, we haven't talked about any of this, but this means that anyone, even without knowing Tau, anyone given the SRS can compute G to the P of Tau. And that's because G to the P of Tau is just a linear combination of these powers of Tau and the exponent, right? So that's G of, I'm just writing out the definition of P here, Ci times Tau to the I, right? Which you can compute this quantity just by applying like the group operation a whole bunch of times to the SRS element. So what is this? Product over I, G to the Tau to the I, which is an SRS element, to the Ci. So if you're not following this, totally fine. Like I'm just sort of free associating aspects of these universal trusted setup SNARKs that you don't need to know about, for our purposes at this point in the book. I'm telling you details of what is the SRS that you just don't need to know, but that maybe you're interested in anyway. I see there's a question that might be coming into the chat, so I'm monitoring that. Okay. So I'd say the downside of these constant round polynomial IRPs other than obviously still having a trusted setup, which, it'd be obviously better if we didn't have them at all. So relative to Groth 16, the proofs are bigger than Groth 16. Perhaps roughly maybe 4 times bigger. 4 to 6, I'd say, roughly. Okay, and here's a statement that I need to be careful about, but I will make. So the prover is slower. Now, okay, I'll read the question in the chat in a second. So prover is slower than Groth 16. Now, here's the care that needs to be taken here. Like for when applied to a circuit or R1CS instance of a given size. So, you give the same circuit to both of them, and the Planck and Marlin prover will be slower than the Groth 16 slower prover. But the counterpoint is that polynomial IOP-based SNARKs, such as Planck and Marlin, but also as the other ones I'm going to describe later, they can use like more general circuits, if you will. And this is when we talked a little bit about Frank-End techniques last week from chapter 6, even though we never assigned that as reading, we talked a little bit about this. So you can think of, if you've heard of Planckish arithmetization, that's what the Zcash people sort of refer to this as. it's sort of using something circuit-like, but the circuits can have operations other than addition and multiplication. They can sort of be higher degree than just degree 2. And so as a result, you can deal with, if you use Planck or Marlin, like the circuit you deal with might be smaller than what you're forced to deal with if you're using Bro 16. And so applying sort of the slower prover to the smaller circuit might be a net win potentially. So that can happen. Sort of in practice these days, to get the small circuit, like the generalized circuit for Planck magnetization, it seems like for things people care about, it's like people are hand coding these circuits. So I sort of want to be clear about something. Like if you look at like the Zcash, I think they just released Orchard. If you look at like the ZK Sync, if you look at these code bases, which I sometimes glance at just to see what's going on, you'll see like thousands of lines of code specifying these sort of hand-rolled circuits. So very innovative, highly engineered stuff, which is really important for concrete efficiency. But counterpoints is that, it could be bug prone, right? So like the zero knowledge proof or, non-zero knowledge SNARK, whatever, that winds up getting applied to the circuit proves the prover correctly evaluated the circuit, basically, right? Applied it to some witness. If you're dealing with the wrong circuit, that statement doesn't actually give you the guarantee you think it does. So you kind of have to trust, like, not just the back end, but that the circuit you're applying the back end to is correct. And so the more complicated the technique to, kind of design the circuit, possibly the more bug prone that is. Okay. Question? Verbal question? And if not, I will read the.
Actually, I have a quick question then.
Yeah, please.
So if do you have any concrete examples from like industry where exactly what you said has happened? So someone had like the prover was generating correct proofs, but the underlying circuit was not corresponding to the native computation that was supposed to correspond to.
No, actually, I haven't heard of that happening. I had not. So, yeah, I don't know how worried about it to be, other than, if I had to just speculate, I would think, these very complicated things, like the Zcash Orchard, I think it literally just got launched in the last couple weeks or something. Oh, no one has had an incentive to try to attack it until now. I'm not saying I think there's an error in it, because like very skilled people were developing that. I'm just sort of making the point that the more, sort of complicated and by hand work goes into the design, and if it's not like formally verified the correctness of, or the more space there is just for bugs to come in, it doesn't really go further than that yet. So I'd say similarly, the roll-up projects that are likely to involve the most complicated circuits are probably the ones targeting, ZK EVM, where they're trying to let people sort of program in Solidity like they do today and just feed that directly through a SNARK. And, that's like the harder compilation problem than like this, Starkware's Cairo, where the programming language itself is like designed to be more SNARK friendly, but there's then more, I guess, burden, if you will, on the programmer to deal with themselves SNARK specific issues. So it's sort of maybe just pushing the burden from the circuit designer to the programmer in a sense. Yeah, so the EVM stuff hasn't really launched yet. I know the ZK Sync testnet is generating these circuits, but I don't know if that gives people an incentive yet to attack it or not. Like, it's a testnet. So anyway, but they're bug bounties. So I don't want to say there's no one's anyway. So my point is, the most complicated, the circuits are getting more complicated like every day, essentially. And I'm sure there are incentives now for people to, look for bugs. But these things are new, and maybe like the biggest incentives, come when the thing actually hits mainnet. That's my general sense of this stuff. And I'm not accusing anyone of having bugs. I'm just making the general point that the more complicated these things get, the bigger space there is for the possibility.
Yeah, that makes sense. Thanks.
Okay, I'm going to read the question in the chat. Okay, so there's the counterpoint is that auditing have to be done only once for ZK EVM, although that will be involved in auditing specific yeah, that, so that's a good point. If you, it's sort of like, auditing the circuit needs to be done kind of once per circuit, if you will. That, by the way, the way a lot of these circuits are sort of getting generated is they're kind of common subroutines people want to handle. So people will design specific circuits for those subroutines. They'll call them gadgets. Yeah. Thank you. Gadgets. And then, so like for Solidity, right? Like, I guess this is at the limit of my knowledge, but EVM bytecode has operations it can do, right? So for each of those operations, some of these rollups are probably hand coding gadgets. And then when someone actually writes a Solidity contract, there's going to be some compiler that sort of glues all the gadgets together that are actually called by that contract. So you have to trust the hand coded gadgets, and then you also have to trust the now automated process to glue them all together. And yeah, like once that's built, you only have to audit it once. Of course, if they ever tweak the gadget because they come up with a better gadget or something, you sort of have to do it again, at least for that gadget. Yeah. So, and I'm really an expert on the back ends, not the front end. So I'm just conveying my own high level senses of these things. But yeah, I think I'm saying things correctly. Okay. I'll move to the BLS question. As a more general question regarding different ZK techniques. You mentioned in the chapter that BLS verification is not super efficient using things like Plonk and Groth 16 due to the need for fast FFTs. What would be a ZK scheme that's better studied for this specific computation? Okay, I don't specifically remember BLS verification being mentioned, although I certainly believe you probably looked more recently than I did. The deal, though, is that if you take any of the Suncheck protocol-based SNARKs, and that's literally like kind of everything I'll tell you about that I haven't written on the whiteboard yet. So and that basically means interactive proofs and multi-prover interactive proofs, which in practice now essentially means like the popular ones. It's basically the interactive proof is the GKR protocol, which we've talked in detail about. The MIP, the multi-prover interactive proof, is basically the one underlying Spartan. Okay, these are the ones people tend to use right now. Although, I mean, as we'll get to it, like people are not using these in like blockchain applications because the proofs are bigger. We'll get there soon. But if you take them, so Sumcheck protocol based SNARKs, that means, IPs and MIPs are the ones that use Sumcheck protocol. And you combine them with the polynomial commitment scheme that is not KZG based, basically. So that means bullet proofs. That means, well, okay, I want to be careful. Not KZG based and not, okay. So there is a variant of IOP based ones. So look, Fry and Lahero commit. I know we haven't talked about any of these commitment schemes yet, but they're IOP based polynomial commitment schemes that do require FFTs. But there's a variant of Lahero commit called breakdown commit, which has even bigger proofs, but like has other nice properties that doesn't require FFTs. Anyway, but IPs plus MIPs using one of the handful of polynomial commitment schemes that don't require FFTs, they will avoid FFTs. Neither component needs FFTs. So the whole SNARK will avoid it. So for very large statements, that FFT tends to be the bottleneck for the prover time. For small statements, as the chapter kind of discussed, other things might be the bottleneck, like, group exponentiations might be the bottleneck over an FFT, even if an FFT is done, if the FFT is small. So yeah, in this context of large enough statements, they don't actually have to be that big, sort of in the cosmic sense. FFTs will be the bottleneck, and so some of these SNARKs that avoid FFTs will be faster. And then just one comment is now people are doing these recursive SNARKs, and that sort of ensures that the statement, if you could apply a recursive SNARK to a pretty big statement, and the base SNARK will wind up never getting applied to a very big statement. So like the recursion is sort of used to break the giant statement up into a bunch of small statements. You apply the base SNARK to the small statements and kind of aggregate the results in a sense inside the proof kind of. And that's another way to sort of ensure that, you know, these things, these operations like FFTs that are very expensive bottlenecks when dealing with very, very big, like a big FFT is very expensive. Recursion can be used to ensure that the FFT itself is never done to something big. You do a lot of small FFTs in that case, essentially. But recursive SNARKs, you know, they sort of naturally apply with minimal overhead settings where you're doing the same thing over and over and over again. But for general computations, you know, breaking a general computation up into a bunch of identical looking pieces can result in giant overhead. So you have to be be careful here, I guess, where the recursive, you know, recursive SNARKs are a way to sort of use a SNARK that does an FFT and apply it to very big statements without paying the price of doing, you know, one giant FFT, but only certain computations can you sort of turn into like something amenable to a recursive SNARK without itself introducing giant overheads. So these sorts of issues are why it's so complicated to compare SNARKs to each other, and why, you know, this chapter is my best effort at it to sort of lay out all the issues. Yeah. Did that answer the question adequately about what would, you know, be a non-FF, something that doesn't incur the FFT? Okay, cool. Great question. And yeah, I hope the answer was useful there. Okay, so at this point in the discussion, we have talked about, sorry for the accidental vertical line. We have talked about Groth 16, which is, you know, great verifier, has a trusted setup, but is circuit specific. Plonk and Marlin, so their big thing really is universal trusted setup. That's like the clear advantage over Groth 16 of them. So let's go on to the sort of, I guess, really the final class of SNARKs, sort of at least organized by the underlying information theoretic protocol, which is MIP-based and IP-based. And at a high level, if you use the, I'd say like the most prover efficient polynomial commitments, with these MIPS and IPs, you know, so you combine the MIP and the IP with the most prover efficient polynomial commitments. Like the big benefit here is you will get the fastest prover SNARK. And yeah, for scalability, like the bottleneck in turn, like, you know, if your SNARK is just going to fall over and like, you know, you're either going to wait too long for it to complete, or the, you know, the prover's going to run out of space. It's the prover that is that bottleneck. So that's why, and this is what my work tends to focus on. And actually, you know, what the book is sort of organized around, starting with, you know, so we do cover all the SNARKs, but, you know, we started with interactive proofs, and next naturally comes multi-prover ones, and then we move to the constant round polynomial. So we do everything in sort of reverse order of how I just covered in the book, maybe ironically. Yes. In terms of what people are using today in the commercial applications, the book is in reverse, literally reverse order, but anyway. So yeah, and I'm hoping, and I do have time to sort of cover in more detail, like why this is the case. Sort of what is it about the MIPS and IPS? No one says IPS, but I'm saying IPS today, IPs, that makes the prover the fastest here. The reason people aren't using these today is because the proofs are big. And I can try to explain sort of why they're bigger. So with MIPS, so the proof length outside, other than the polynomial commitment. Is going to be like order log circuit size or log number of constraints in the R1CS that you're dealing with. So S here is, let's just talk about circuits. S is circuit size. We're dealing with circuit size. S is circuit size. For the GKR protocol, this log S is depth of the circuit times log S. Really, it's log width. I'll write that out, log width. Okay, and this is always worse than, at least up to a constant factor, than log S. So the IPs have the biggest proofs, and the MIPs have the next biggest proofs after them. And that's basically why people don't use this stuff, like regardless of polynomial commitments can use, because like, so you can combine either of these with KZG based commitments, and actually then you would need multilinear polynomial commitments, and actually even KZG based polynomial commitments have log size proofs coming from the polynomial commitment scheme in the multilinear case. But even if you had a constant size proof from your polynomial commitment scheme, if you combine it with a MIP or an IP, the proof length is just going to be bigger. It's going to be at least logarithmic in the circuit size, whereas everything else above, so Planck, Marlin, Groth 16, it's constant. So that's what's going on here is ignoring the cost of the polynomial commitment, the proofs are just bigger in the MIPS and the IPs. And then like on top of that, the fastest prover polynomial commitment schemes themselves tend to have big proofs. So the fastest ones have square root size proofs. So if you apply them to a polynomial, of degree D, or a multilinear polynomial with log D variables, so that means, D coefficients. So like the size of the polynomial is D, the evaluation proofs will have size square roots for the polynomial commitment, square root size proofs. Right. So, in short, it sort of makes sense that there's a trade-off between verification costs and proving costs. So the fastest known prover SNARKs have bigger proofs, both because outside of the polynomial commitment scheme, you have these, roughly logarithmic size proofs. But if you're using the GKR protocol, there's also this factor of the circuit depth, which is sort of even worse. And on top of that, the fastest for the prover polynomial commitment schemes have big proofs. And will tend to dominate the proof size if they're square root size, because square root is worse than log, basically. And that's why people aren't using the MIPS and IPs in like blockchain stuff now. What else do I want to say? Yeah, okay. And just briefly, the reason that the IPs can have faster prover than MIPS is basically the polynomial commitments in MIPS, polynomial commitment in the MIPS is applied to the whole circuit. So like there's like a vector of gate values, one for every gate in the circuit. And that's interpreted as like all evaluations of some polynomial over the Boolean hypercube. And yeah, so the vector you're taking the multilinear extension of is as big as the whole circuit. So that's what I mean by the polynomial commitment scheme is applied to the whole circuit. So vector of size S, by that I mean like the coefficient vector of the polynomial has size equal to like the whole circuit. Remember that circuit size is S. Okay. Whereas for the GKR protocol, so GKR is the interactive proof, GKR IP, that vector has just size, it's just the witness to the circuit. So by witness, I mean, the claim is that C of X comma W equals Y, where here X is the public input and W is, we talked about this last week, the witness to the circuit, which includes not only like the prover's private input, but also advice elements. So witness to circuit, which if you were here last week, that witness to the circuit tends to include like the actual, what people will call the witness of the application, call private input, to not use the word witness twice, plus advice inputs. which are sort of used to compile to a small circuit instead of a giant circuit. So that's the benefit of, for sort of the prover time of the GKR protocol, is the polynomial commitment scheme is getting applied to a shorter vector. So if the witness to the circuit is like not is only a small fraction of the whole circuit, that's a much shorter vector than if you use a. But in general, like if you look at the efficient, front-end techniques from computer programs to circuit sat instances from chapter 6, those general techniques all, yield witnesses that are really big, a constant fraction of the circuit. So the savings of this in practice, it might not be significant. And this is another complicated comparison point is, there are papers on the, using the GKR protocol for SNARKs, which my research was one of them that introduced that. So I'm a fan of it. But in general, so there are papers that will apply this to circuits with small witnesses and say look how fast the prover is. But it's not clear to me that the circuit that they're using is as small as the circuit they could have been using if they allowed the. So you wind up with this trade-off again, is tension, where if you might generate a circuit with a small witness, and then the GKR protocol looks great for the prover because the polynomial commitment scheme is applied to something really small, but you're actually using a bigger circuit. So did you come out ahead or not? It's not clear. And then if the GKR protocol has a bigger proof because of this dependence on the depth that's nasty than if you had used a MIC, where the polynomial commitment is applied to the whole circuit, but then the proof is shorter. Remember, the depth of any Fanon-2 circuit is always logs, at least log number of inputs anyway. So it was probably log circuit size actually in general. So depth times log width is always worse than log circuit size. It might not be that much worse. Anyway, in practice, it's worse. Can be significantly worse, in order of magnitude or more. So there's this tension. If your witness is the witness to the circuit is really small, GKR is going to save prover time significantly, potentially, relative to using a MIP. But to support general compilation to small circuits, you in general need big witnesses, and then it's not really saving you that much. So that's the comparison there. Okay, I'm going to pause for questions, and then sort of the technical thing I wanted to try to explain today, because it's sort of spread over several parts of the book, is kind of why sort of the Planck and Marlin, the constant around polynomial IOP based SNARKs, but I'll just write out Planck and Marlin because those are what people use. Planck plus Marlin prover at a technical level is slower than MIP or GKR prover. Because this is subtle. I don't think I even really appreciated this until, embarrassingly recently, not yesterday, but, what the technical reason was. So I'll go ahead and explain that, but let me see if there are any questions. For IOPs, what is the proof length generally? Isn't it logarithm? So, okay, you have to be careful what you mean by IOPs here, because so it's a useful abstraction to talk about polynomial IOPs. What these are interactive proofs, if you will, where some of the messages from the prover to the verifier specify polynomials that are really big to specify. Okay, so in practice, if the prover was literally going to send a specification of that polynomial to the verifier, it would the verifier reading that specification would take as long as just evaluating the circuit on her own. Sorry, let me turn my phone off. Who that was? Yeah, I think that was a butt dial. Okay, so anyway, that's a polynomial IOP. And so the way you get a SNARK out of a polynomial IOP is, rather than having the prover actually send these giant polynomial description to the verifier, instead the prover cryptographically commit to these polynomials with the polynomial commitment scheme, So the prover is just sending like one cryptographic hash value or one cryptographic group element to commit to the giant polynomial. And then the polynomial IOP verifier, turns out you have to design the protocol so that the verifier only needs to evaluate that committed polynomial at like 1 or 2 or 3 points, and it gets the evaluations out of the commitment scheme. So like a description of the whole polynomial never needs to get sent to the verifier. Okay, and then an IOP itself doesn't allow for these special messages that specify a giant polynomial that, like, in the real world get replaced with polynomial. In an IOP, it does allow special messages, but there's no guarantee that message specifies a polynomial. So the special messages in an IOP, what that is in an IOP, it's just a string. It's a long string that the verifier doesn't want to read in entirety, but there's no promise that that string is like all evaluations of a polynomial. Okay, so the main useful point of IOPs themselves, it turns out, sort of if you actually look at like the protocols people are using, is to give a polynomial commitment scheme that so the way that works is you give it an IOP, like a real, like not a polynomial IOP, an IOP, and you can turn in an IOP directly into a SNARK, like just with Merkle hashing. So we kind of discussed this last week, where like Merkle hashing alone will bind the prover to a string, but will not give the verifier any guarantee about the content of that string. So if you wanted a polynomial commitment scheme directly from Merkle hashing, you'd have to combine it with a low degree test to make sure that, like, so as we discussed last week, like a naive way to try to get a polynomial commitment scheme is to have the prover commit to like the string of all evaluations of the polynomial. Now that's totally impractical, but like just in terms of the cost, because that string is so long, but let's just ignore that. But if you just Merkle hash that string, the verifier doesn't know that, the committed evaluations are actually evaluations of a polynomial. It's just like, some unstructured list of its function evaluations. So you need a way to test that they're actually consistent with the low degree polynomial. Whereas, so what these IOPs do is they kind of give a way to do that testing without using an interactive version of a low degree test, where the verifier can send a random challenge to the prover as it tries to figure out committed evaluations consistent with the low degree polynomial or not. And so there are basically only two IOP based polynomial commitment schemes to know about. They're both discussed in chapter 10, which is the IOP chapter of the book. The most popular one in practice is Fry. That's because it's the only one with reasonably short proofs. The other is Ligero and Breakdown, which are kind of really the same scheme, but just differ in sort of what error correcting code they use under the hood. But anyway, that's square root size proofs. And that has a faster prover than Fry, significantly so, but much bigger proofs, like much big too. Okay, so what is the proof length of Fry? It's not log, it's polylog. So I think it's actually the security parameter lambda times, I believe, log squared of the number of coefficients of the polynomial. So that's polylog, but it's kind of like, in practice, pretty big proofs, especially in a blockchain context where these proofs are getting posted on chain. You're paying gas for that. So that's Fry. And Ligero and Breakdown, it's the cost is roughly order square root of lambda times n, where n is the size of the polynomial, the square roots over both of them if you do the right optimizations. And so it's actually a slightly nicer dependence on lambda, but vastly worse dependence on n. So the proofs are much bigger. Okay. So that's the trade-off there. So apologies that the answer to your question was so long. So basically for constant round polynomial IOPs, the proof length is like a constant number of polynomials, but the polynomials themselves are really big. So you're going to replace them with a polynomial commitment scheme that's going to have its own like proof lengths. And if that commitment scheme is IOP based, it's going to be Fry or Ligero, and those proof lengths from the polynomial commitment scheme are going to be like log squared or square root. Indeed, so the size of the proof is mainly the one from the IOP commitment scheme that's bigger in the case of MIPS. Yeah, so this is, if you combine a MIP with Fry or Laharo polycommit, okay, the MIP is going to have log proof size ignoring the polycommit. And then the polycommit is going to have like log squared or square root proof size. So in using those polynomial commitment schemes, there's like no reason not to use the MIP, essentially, right? Because the polycommit is going to dominate the proof size over the logarithmic contribution of, outside the polycommit. This is actually, someone should actually sit down and compare. So fractal, which is like, I guess from the Starkware folks, I guess, certainly there's some overlap at a minimum. Fractal combines the Marlin polynomial IOP roughly with Fry. Yeah, so, well, yeah, but so Alessandro is from Berkeley, but also involved with Starkware. So, yeah. So, okay, let me call Fractal the Berkeley folks and say the Starkware folks, and I don't know how the details of the overlap. Anyway, so yeah, it's kind of like takes the Marlin polynomial IOP, replaces KZG commits with Fractal, and then does a bunch of optimizations to, sort of optimize given the fact that they're using Fractal. And yeah, so like outside of the polynomial commitment there, like the proof length is constant because it's a constant round polynomial IOP underlying Marlin. So what's dominating there is the use of Fry as the polynomial. So, someone really should implement, they might have, but like, the Spartan polynomial IOP, but using Fry as the commitment scheme. Okay, now you run into you do run into a complication that Fry is targeted at univariate polynomials. There is a known technique, which is discussed in the book, to sort of port Fry over to multilinear polynomials, which is what you need to use MIP. It introduces some extra overheads. The works that have done that are used GKR and not Spark. So I'm not sure someone has actually gone down and implemented this particular combination of MIP plus the multilinear, porting of Fry. Someone should do that and compare to Fractal. And my guess is the prover will be better than Fractal because, well, we're going to I'm hoping to not run out of time, although I'm almost out of time, and discuss some of the reasons for that. That would be great. Yeah. So, the Spartan code is online. It might not be place the polynomial commitment with what Spartan actually uses. Just plug in. Right. Actually, it would be tedious. It's just you can do it, but yeah, we don't have to get into the details. Okay. So sorry that was such a digression. But basically, these polynomial IOPs, they have two contributions to the proof length. There's like the proofs ignoring the polynomial commitment and the polynomial commitment, and depending on the polynomial commitment used, the polynomial commitment might or might not dominate the proof length. If it does, then there's really no reason to worry about the larger proof length of MIPS and IPs, sort of outside the polynomial commitment. It's just, if you really want to minimize proof size, as many of the blockchain projects do, you want to use a constant round polynomial IOP and KZG commitments because both of those, both contributions to the proof length are minimal there. You got a constant round polynomial IOP instead of logarithmic or worse, depth times log width. And the polynomial commitment is like the shortest proof length polynomial commitment is KZG, just a constant number of group elements. So, but what if you're in some setting where you don't mind larger proofs, you wind up with a nicer prover if you select both the polynomial IOP and the polynomial commitment to both be nice for the prover. Okay, there's a question here, the text mentioned by taking a fast prover, larger prover. Okay, yeah. What are some obstacles achieving this right now? Yeah, so thank you. I wanted to mention composition. Yeah, so I hope, my personal hope as somebody who has kind of devoted a third of their life to working on the fast prover stuff, is that there's a way to sort of get the best of all worlds, which is to take the fast prover snarks that have bigger proofs and just do one composition. So not any kind of like deep recursive kind of thing, just one composition with a small proof, possibly slower prover snark to get a resulting snark that has like the small proof of the one snark and the fast prover of the big snark. What are some obstacles of achieving this right now? I don't actually, I think this should succeed. And in fact, well, I don't want to, I've been working on this for a while. I've heard some other people are as well. Fortunately, I think there is not actually literally the same approach. I hope there's some differences, obviously, so that we can all, aren't duplicating work. What's taking my work so long is it's just really tedious to take a SNARK verifier represented as a small circuit and feed that through a small proof SNARK, which is what happens in composition. So you have to go through this tedious exercise once of taking the verifier of one SNARK, representing it as a circuit that you can then feed into another SNARK. And we've just been very, very slow to do that. It's just like a couple researchers. Now, what we might discover that there are technical challenges too, where we just can't get the circuit to be that small, right? So like taking a SNARK verifier and representing it as a circuit could just be a nasty task. So what do SNARK verifiers tend to do? They tend to do group exponentiations and Merkle hashing. And the group exponentiation, these groups are elliptic curve based. So you have to actually, take elliptic curve arithmetic and represent that as a circuit. If there's Merkle hashing involved, you have to take cryptographic hashing and represent that as a circuit. And if you're not careful in the group you choose or the hash function you use, the circuit's going to be really big. And then, the cost won't look good in practice. So, but I think all these things are surmountable, and I hope it won't be that long before we get some really nice snarks where, maybe they don't have the smallest proofs out there, but the prover is faster, and, maybe they're transparent, and where Marlin and Planck and Bro 16 are not transparent. So we will see. And I guess something to mention in like the rollup context is, these rollups might be latency bottlenecked where like, so the, the gas cost saving, like the gas cost for these rollups amortized, there are two contributors to it. There's like, how expensive is it to verify a proof on chain? So for that, to keep that low, you want the SNARK verifier to be really, really fast and simple. And then there's how many transactions can one proof aggregate? And, given that these SNARK provers are pretty slow, like the fact that people don't want to wait that long for their transaction to be finalized on the L1 might be the bottleneck in terms of how big we can make these batches. So it might be better to have a bigger proof SNARK, slightly bigger proof, can't be vastly bigger, if the prover is way faster, because that might let you take the batch size bigger, without having people waiting around for days or something, And hence you might get better amortized savings with a slightly big, slower verifier if the prover is much faster. So yeah, these are my grand hopes. We'll see how things work in practice. Hopefully that answered your question. And that's why like the book is like vague and says a few sentences, but I was really hoping by now to actually have a paper online to then point to in the book and be like, look, this is great. This is the way really people should be doing things, unless they really, really, really need the smallest proofs out there or something. And unfortunately, it's just taken forever. So, okay. I probably shouldn't try to give the technical reason, given the timing, why, the prover in the cost round polynomial IPs tends to be slower than the MIPS and the IPs. But I can say one sentence about it. And basically, here it is. So in the multi-variate sum check protocol, by which I mean, let me put that in parentheses. What you know as a sum check protocol, because we discussed it in chapter 4. When you use this, like basically when you use this in the context of a SNARK, like it ensures, base SNARKs. it turns out the prover only needs to commit to one polynomial. Okay, so we've seen one complete SNARK of this form, which is GKR protocol plus polynomial commitment. And so for that, for like GKR based, we actually saw this in chapter 7, like the prover commits to just the multilinear extension of the witness. The multilinear extension of the witness, right? Just that one polynomial. Okay, and then like all of the rest of the prover work is like pushed into the sum-check protocol and happens, you know, at certain inside the information theoretically secure protocol. Okay. Now, if you look at Planck and Marlin and probably any other constant round polynomial IOP you come up with, the prover has to commit to many polynomials. That, I mean, in a sentence, you know, without going into details, I can't tell you all the subtleties here, but that's what's going on in the sentence. And many can mean like 10 or more. I think in Planck, it's like really a lot. Now, if a lot of these polynomial commitment schemes have really nice batching properties, which basically means kind of you don't need to, the verifier doesn't actually need to like independently evaluate each of the committed polynomials at a different point. They can kind of pay, the verifier is going to wind up paying only for one commitment, not like 10 or more of them. So the verification costs of Planck and Marlin are not like 10 times, you know, 10, 20, 30. It's not 10, 20, 30 times more than gross 16 or anything like that. But the prover is slower, you know, again, up to these caveats about being able to use generalized circuits, and they can be smaller than. So that's the difference, basically. That's where it comes from. So, and maybe next week I can say more about why this is happening. So for the prover, you know, if the polynomial commitment is the bottleneck for the prover time, especially here, you're getting a prover that commits to only one polynomial, which is either as big as the witness or as big as the circuit. And in Planck and Marlin, the prover is committing to like 10 plus polynomials, each of them as big as like the whole circuit. So that's where the extra prover costs are coming. But on the other hand, because, you know, outside of the polynomial IOP, the proof is much shorter in Planck and Marlin. It's constant instead of log. So if you're optimizing for proof size, you're definitely going to get much shorter proof out of Planck and Marlin for proof size. So those are the trade-offs. And yeah, maybe in future, we'll see, you know, again, these faster proof or bigger proof things get composed successfully, concretely with other SNARKs. And maybe we'll have some alternatives to Planck and Marlin that people find attractive. Remains to be seen, since at least I haven't succeeded in completing the implementation yet. So, okay, that's everything I wanted to say today. If you want to ask questions, I can stick around a bit. I think baby's asleep before I have to get back on that. But otherwise, maybe in the chat, if I guess we'll just default to just meeting at the same time, but keeping the meeting 30 minutes next week. Okay, looks like I'm good to go. I see people typing, so it looks like there'll be more discussion in the chat, which is fine. And I'll definitely get to any more chatting by tonight, let's say. So, yep, I'm going to sign off the recording and talk to you all next week.